All right, let's jump right into this. We're talking about a potential breakthrough that could completely change how we think about computing. Imagine taking the incredible power of a quantum computer and shrinking it from a massive, super cool laboratory down onto a single tiny chip. And that really is the heart of the matter, isn't it? It's the question that has kept engineers and physicists up at night for years. How in the world do you get the phenomenal problem-solving power of a quantum computer without the giant, incredibly fragile, and absurdly cold freezers they need to operate? You know, when it comes to humanity's hardest problems, we've been stuck between a rock and a hard place. On one hand, you've got these cryogenic quantum systems. They can do amazing things, but you have to cool them to temperatures colder than deep space. On the other hand, you've got our trusty classical supercomputers. They work just fine at room temperature, but they often get completely bogged down on these complex problems, and they use an absolutely enormous amount of energy. So what kind of hard problems are we actually talking about? Well, these are the big ones, the kinds of challenges that could help us discover new medicines, invent revolutionary new materials, or optimize global supply chains. I think the best way to picture this is with an analogy. This whole class of problems is called combinatorial optimization, and it's a lot like being dropped into a colossal mountain range, completely blanketed in thick fog, and your one job is to find the absolute lowest point, the deepest valley, in the entire range. So, how does a classical computer try to solve this? It basically just starts walking downhill from wherever it lands. It finds a valley and says, okay, I'm at the bottom, this must be it. It gets trapped in what we call a local minimum, totally blind to the fact that a much, much deeper valley, the real answer, might be just over the next ridge. But a quantum computer has a superpower. It's called quantum tunneling. It doesn't have to waste time climbing all those mountains. It can just, poof, pass straight through them. This allows it to explore the entire landscape almost all at once to find the true global minimum. This is their killer advantage, but it only works inside those crazy cold freezers. But what if there was another way? A third option? What if you could somehow build a bridge between these two worlds and get that incredible quantum-like exploration without all the quantum hardware? Well, it turns out there's a really deep principle, a secret connection buried in the math of physics that's actually been known for decades. And here's where it gets really, really interesting. This connection suggests that you don't actually need a true quantum system to get quantum-like behavior. You just need a classical system that's cleverly designed to act like a quantum one. And this is it. It's called the Suzuki Trotter equivalence. Think of it as a theoretical blueprint. It's the mathematical proof that shows you can perfectly mirror the behavior of a quantum system with a classical one, as long as you build it in a very specific way. This idea is the key that unlocks this whole new approach. Okay, so a theory is one thing, but what happens when a team of researchers actually takes that blueprint and builds something real? Well, that's exactly what happened. They created a brand new type of processor based entirely on this principle. They call it Apollo. It's a neuromorphic processor with 10,000 nodes, designed from the ground up to solve these huge problems, all on a chip that works at room temperature. And at its very core, it's not using a classical bit or a quantum bit. It's using something new, something in between. This is the p-qubit, or probabilistic qubit. Now, it's a classical component. It's always either a solid 0 or a solid 1. But here's the twist. It flips between those two states incredibly fast. And that flipping isn't just random noise. It's being driven by a true source of quantum randomness that's happening right there on the chip. This visual really shows you where the p-qubit fits in. On one end, you have a classical bit, just stuck as a 0 or a 1. On the other end, a superconducting qubit, which exists in that fragile state of being both at once, a superposition. The p-qubits carves out this brilliant middle ground. It rapidly jumps between 0 and 1, harnessing real quantum randomness to explore possibilities, but without needing that delicate quantum coherence. And because at its heart it's a classical system, the amount of power it needs is just astonishingly low. We're talking about half a watt. So let's just put that all together. We're looking at a chip that delivers quantum-like performance. It runs at room temperature, and it uses less power than the little charger you plug your smartphone into. I mean, the leap in efficiency is almost hard to wrap your head around. Of course, making a claim like that is one thing. Proving it is something else entirely. So the big question is, how does this radical new chip actually stack up against those multi-million-dollar cryogenic machines? So the researchers put Apollo through its paces. They tested it on a classic hard problem called the 3D spin glass problem. This is the exact same benchmark that's used to prove whether the big superconducting annealers have a true quantum advantage. This was a real apples-to-apples fight.
And the results were stunning. The research paper states that Apollo's performance showed scaling trajectories that were, and I am quoting directly here, indistinguishable from the cryogenic quantum hardware. In other words, the little room temperature chip performed right on par with the giant, freezer-sized quantum computer.
And in some really important ways, it's actually better. When you're trying to map a complex real-world problem onto a processor, connectivity is everything. You need the different parts to be able to talk to each other. Apollo's architecture allows for 256 connections per node. That's more than 10 times better than current quantum systems. This means it's way more efficient at actually setting up and running a problem in the first place. So, what does all this mean? Where do we go from here? This isn't just about a faster, more efficient chip. This really feels like a paradigm shift in what's possible and who gets access to this kind of computational power. The potential applications are just staggering. We are talking about accelerating drug discovery, designing revolutionary new materials, creating smarter financial models, and maybe even training the next generations of AI. All of these huge fields are bottlenecked by exactly these types of massive optimization problems. And that leaves us with one final fascinating question. For decades, quantum-scale computing has been locked away, the exclusive domain of giant corporations and government labs. This technology points toward a future where that same power could be accessible, efficient, and scalable. So you have to wonder, what new frontiers will we cross when the power to solve the unsolvable fits on a single chip?